Okay, let's continue with this slide here. This is slide 14. Um, and this is where we're having a circular runout tolerance with one datum feature. Okay, so references to one datum feature is often enough. Okay, in this case, we have datum A here as the diameter, and then we have these two diameters that have runout tolerances of 6 thousandths relative to datum A. Proper datum feature selection is essential for verification and low product cost. Now again, when we're checking these parts, what we need to be sure of is that we're grabbing this diameter regardless of material boundary. So we're going to pick that diameter up essentially regardless of feature size, in which case we would have to use a chuck or something like that. And then over in this case, what we have here is our datum feature, our axis of revolution datum feature here is an internal surface. So we're going to have an expander plug or something that comes in here and touches this diameter here regardless of its material boundary. So keep that in mind with runouts. These are always RMB and always RFS. Okay, common datum features. We talked about this before, but it's where you got two or more features are used to establish a single datum, and it's indicated in the feature control frame with a hyphen between the datum feature reference letters. And then these are defined by referencing two or more datums at the same precedence level. Okay, so here is how that looks. Okay, so we've got this part. We're establishing our axis of rotation actually via two datums, datum B and datum A. And then using those as common datums, we reference that in our feature control frame with A/B. So the axis of rotation is established by two features, and then both of those datum features will be used simultaneously to establish the datum axis. Now, we can also use common datum features if they're internal features too. It's like coaxial holes, for instance, may be used to establish a common datum axis. It's possible to use non-functional features as datum features. Consider the accumulation of tolerances between non-functional and functional features. That's why we always like to use functional features, because that's how our tolerances do not accumulate. And then we can also use common datum features as targets. In this particular case, we have datum targets here. We've got datum A, A1, A2, A3, and then B1, B2, B3. These are targets. So the 3 points will center up that cylinder about its axis. So when specific locations on features must be used to establish a datum axis, and that's what you do with these targets. These are specific features that are used to establish the datum axis. Now, functional datum features may be large enough to make contact with the whole feature in practical. Therefore, irregular features will always require these specific locations selected. If it was just a cylinder, you can grab it with a chuck. Okay, well, if it's irregular or we have to control the points where we make contact here, then we'll use datum targets to specify our common datum features. Okay, so let's talk about runout reference to a primary and a secondary datum. In some cases, applications require a secondary datum to stabilize the part, and it must include one datum axis and then a second datum axis. Whether an axis or plane is primary depends on the design function. Okay, but let's look at this case in particular. We have our datum of rotation that sets up the rotational axis of datum A here. And then we're also using datum B, see, not as a common, but as a separate datum reference here, and we're checking the runout to that. So the difference for us in this particular case, in terms of simulating this, would be to use the chuck jaws that pick up datum A regardless of material boundary. Essentially, chuck on it regardless of what size it is. But then we also have to have this datum surface B here square up to the face of the chuck. We need datum B to make contact with the datum simulator, which would be the face of the chuck. So this is the difference between two datums and just one. I think think, let me show you another picture from before. Like this one right here. When we were checking the face surfaces, we noticed that this face of this chuck is not making contact with the part, and that we're only picking up datum A as our rotational axis here, and we're not touching the face. So again, that would be just a little bit different than what we're looking at right here. When we have to have this other datum reference, we need to make contact with the face of the chuck. Let's talk about total runout. Now, I kind of look at total runout versus circular runout, kind of like when we talked about the difference between straightness and flatness. Okay, straightness applies to individual line elements on a surface, kind of like what the circular runout does. And then, when you went to flatness, you're evaluating all of those elements simultaneously. So it kind of means the same thing. So total runout is the variation across the entire surface of a feature or part relative to an axis of rotation. And in contrast to circular runout, with total runout, all surface elements are going to be evaluated together. So the allowable form, orientation, and location of cylindrical or flat surfaces elements are relative to this axis of rotation. Now with this one, the tolerance value is not limited by the size limits. And then full indicator movement caused by surface variations across the entire feature, that is the total runout variation. Okay, so what we would be doing is spinning the part and then scanning the indicator back and forth to get a total runout reading. Okay, so let's take a peek at what a feature control frame would look like for total runout. So you got the tolerance symbol first. Okay, total runout is 2 arrows. Okay, diameter symbol is never applied because we don't apply these tolerances to features of size. We only apply them to surfaces. And then always applied regardless of feature size. There is never any modifiers in here. And the datum feature references are made in the same manner as circular runout. That means they are always applied regardless of material boundary. So how do we put this on the drawing? How do we specify this? Okay, in this case, here's our model. We have a common datum axis A, B is set up, and then we use a leader with a dot to apply the total runout tolerance to that surface. On an orthographic view, here's how we would do it. We would have our datum A and datum B set up as a compound datum. We can apply the runout tolerance with a leader pointing to the surface, or we can take an extension line from that surface and apply the tolerance to that extension line. That's the other way to do it. And then we could also do this with internal features as well. Our datum C in this case is an internal feature, and then we have a runout tolerance of 6/1000 to datum C. Now we can also apply total runout to face surfaces, kind of like what we did before. In this example here, we're using the axis of revolution as datum A, and we also have a face here, surface for datum B. And how we're going to go, and then we have a total runout here on the opposite face of B. And then our feature control frame goes to A and B, in which case we need to chuck up on datum A, and then we'll touch the face with datum B here to simulate datum B, and then we will scan our indicator while we're rotating the part. We'll scan our indicator across the face and check for our full indicator movement reading. I just got a few more slides, but I don't want to make this movie very much longer, so I'm going to break it up into another movie. Thank you.